this video I'm going to look at the Leaving Cert Applied Maths question 4 2008b. This is a really long question and it's the first time we've done a question like this, so I'll probably split this video into two. Okay, so in the first video what I'll do is I'll do part 1, which is basically just showing showing the forces acting on the wedge and the other particles, and in the second video I'll look at part 2 depending on how long this video takes. So let's have a look at the question. We have two particles, one has a mass 2m, the other has a mass m. They're connected by a light, inextensible string which passes over a smooth pulley at the vertex of a wedge-shaped block. One particle resting on each of the smooth faces. The mass of the wedge is 4m. The inclination of each particle to the horizontal is 30 degrees. The wedge rests on a smooth horizontal surface and the system is released from rest. So there's a couple of things here. First of all, the use of the word smooth means that there's going to be no friction for our 2m particle and our m particle. And the second thing is that they've actually told us that the wedge is on a smooth surface. So that means this surface is smooth. So that means there's no friction whatsoever. And usually, or up until now, we've looked at questions really where there is friction. But if there's no friction, that implies that this wedge itself might actually start to move. So let's look at the first part, the forces acting on each diagram. So we look at the wedge first. And sorry, my drawings are bad, but you're used to that. So the wedge has its weight, which will be mass times gravity, 4mg down. It's going to have a reaction force from the ground. It's going to have, because it has a pulley here, this pulley is actually considered part of the wedge. So we have to include the forces here. And because that string is acting over it, like so, what you're going to have is you're going to have a tension force pulling on the pulley in this direction and a tension force pulling on the pulley in this direction as well. But because it's the same string, those tension forces will be equal. We have a 2m particle here, so that's going to push in as well, and we'll call that reaction force 1 because it's going to be as a result of the weight that the 2m particle is pushing down. And we'll call this reaction force 2. So that's the force diagram for the wedge. Let's now have a look at the force diagram for the 2m particle. So for the 2m particle, here, first force is going to be its weight, which is 2mg. We can split that up into components which are perpendicular and horizontal to the plane. So we'll have 2mg cos 30 and we'll have 2mg sin 30. It's being pulled up in this direction by the string, so we have tension. And there's going to be a reaction force here as well. So we're also going to have a reaction force. Now here's the key bit here that's new, I suppose. We're going to call this reaction force R1. And that reaction force R1 is the same as this R1 here that's acting on the wedge. They're the same force, they're the same size. In previous questions, we've looked at this situation where the wedge is not moving, and we were able to say that R1 is equal to 2mg cos 30. But in this question we can't. And the reason we can't is because when you look at this wedge, when you look at this whole situation, obviously there's going to be a force pushing down it here, R1, and a force pushing down it here, R2. Both of those forces, and hang on, I'll make this a bit better angle. Both of those forces are going to have horizontal components. So R1 is going to have a component in this direction, and R2 is going to have a component in this direction. We're going to assume that one of them is bigger than the other because it has to be, because this angle is the same on both sides and this has a mass of 2m, whereas this particle has a mass of 2m. So if we assume that the 2m component in the horizontal direction is bigger, that tells us that this whole wedge is going to move to the right. It's going to have an acceleration causing it to move to the right because this component will be bigger than this component. Now they're not the only horizontal forces acting on it. You could look at the t and say that, well, the t is going to have a horizontal component in this direction and a horizontal component in this direction. But because these are the same angles and because this T and this T are the same, those forces will cancel each other out. So really the only horizontal forces that matter are the horizontal components of R1 and R2. So really important that R1 is not equal to 2mg cos 30. And it's the same as when you have something on a table, well then its weight, mg, is equal to its reaction force. They're equal because it's not moving. But if something is accelerating downwards, if something is moving downwards, and let's say there's a downward force mg and an upward force, let's call it p, well, because it's accelerating downwards, we cannot say that they're equal. mg must be greater than p in this case. So that's just a little side note, that's not part of the question obviously. So they're all our forces for the 2m particle. Let's go now and do the last particle, the m particle. So the m particle is at a kind of angle like this. Again, its mass is going to be mg. Sorry, I know that's not very straight. We can split that. Its weight, sorry, would be mass times gravity. Split that into a component which is parallel with the plane, which will be mg sine 30. And perpendicular to the plane, mg cos 30. T is going to be pulling it up in this direction, and we're going to have R2. And remember again, R2 is not equal to mg sine 30 in this case. It's going to be different. So there are force diagrams. So first of all, make sure you're happy with that. And what I suggest you actually do maybe is pause it, turn the page and try and do it again yourself, just to make sure that your force diagrams are okay.